Hello, and welcome back to another episode of Corks and Quarter Notes. Today, Tyler and I will be talking about cosmology, the Big Bang, conceptualizing infinities, and the limits of language when talking about these subjects. As always, if you enjoy the podcast and would like to show your support, you can follow or subscribe on your respective podcast platform, as well as leave us feedback in the form of reviews and comments. So as always, we like to define our terms. So what is cosmology?
Cosmology is just studying the universe as a whole system rather than studying the individual parts of it.
So universe, when you say universe, this word is a little bit slippery. We used to think the solar system was the universe and then the Milky Way was the universe. So like, what would you describe as the universe?
Probably everything we're able to see.
So you would say the observable universe is the universe, or?
Right. Yeah. At least for when discussing cosmology.
So this is weird, but we assume like there's more of the universe outside of the observable universe, right? Or no?
If we are to believe inflation is correct, it makes predictions that we are only but a small part of the entirety of the universe, yes.
But at that point, we are just kind of speculating since we can't actually see anything outside of the observer.
Right, yeah. There's a hard limit to how far we can see.
Now, this might be jumping ahead, but we've talked before about the idea of like multiverses and such. Would other universes other than this, so is one way of thinking about that of another universe as just like more of what's here but outside of what we can observe, and then that would be actually a different universe altogether?
Yeah, so the way I think about this particular type of like multiverse, it's like you can imagine you're in a forest and you can only see so far into the forest, and like somebody like 2 miles away or whatever, they're completely obscured from you and they can't see you either, but y'all are both kind of in the same place. And I think that's a type of universe that inflation describes, is just this enormous region of space with stuff in it, and then we only see this small bubble, and that small bubble is what we call our observable universe.
Gotcha. I've always looked at it like being on the open sea, because we're in the middle of observable space, obviously, because it's like we're in the sea, we're looking out in every direction, and there's a limit to how far we can see.
Right, yeah, yeah.
But when we're talking about cosmology, we're not necessarily talking about all these different areas of potentially observable universe. We are just talking about everything we can see as far as we can see it, and then that's what we're talking about.
Right. Cosmologists try to model like everything we can see as a whole.
So that picture can kind of change then. So cosmologists today are doing very different work from cosmologists like 20 years ago.
Well, it's like the same work, we just have better data, right? And I would say cosmology is probably it's fairly new as a subject or a study. We just we haven't had the data to look further than a few galaxies or past the Milky Way.
Right. So how is cosmology different from, say, like astrophysics?
So an astrophysicist would study like individual pieces, say like how galaxies evolve, maybe how stars evolve, stellar objects. They just look at the individual components. They're not looking at the overarching system that they're embedded in.
So they're actually like pretty different ideas then.
Oh yeah. Whenever you take like an astrophysics course, the physics and math that you use is different than cosmology.
It's almost like the difference between someone who studies fish and someone who studies the entire ecosystem of the ocean, sort of.
Something like that, yeah.
So where do we start?
I suppose we could start with our current best understanding, the Big Bang Theory, not the TV show. So the Big Bang Theory is more of an observational theory. We know that the stuff in the universe a long time ago was really close to each other, and it's currently how do you say, quite sparse, spread out. There's a lot of space between stuff that didn't used to be there.
Well, so how do we know that? How do we know that it used to be all condensed?
Just observation. Like we look, and what we see right now is that everything else is flying away from each other, essentially. We just extrapolate backwards. We say if it's going away from each other right now, it was probably headed towards each other if you go backwards in time. And we can follow that. And if our models are correct, we can go back about 14 billion years before everything is literally just at the same point.
So to go back a little bit to how we were talking about the observable universe and how there might be other pockets of the observable universe. We're talking about the Big Bang thing. We're talking about the beginning of what we can observe, not necessarily the beginning of everything.
Yeah, it's hard to say if the Big Bang was the beginning or if it was just like the beginning of a new era or something like that.
It's definitely the beginning of everything we can see.
It's
right
definitely
now.
the beginning of something.
Yeah.
Right. Right. But I don't know if it's like the ultimate true beginning.
But like there could be, say, like a Big Bang here, and there could be another region of observable space beyond what we can see, and there could be another Big Bang that happened there, and so on and so forth. Like that's not out of the picture necessarily. Even though we are talking about everything in some sense, we're not talking
Right.
about everything. I don't.
So from what I understand, and so I'm going to lean heavily on inflation theory because that's our current best explanation, at least widely accepted. I wouldn't say it's the only one. So according to inflation, what we see isn't everything. If you go really far away from us, you will be at the center of some of a different observable universe, if that makes sense.
Well, in some sense, every time you move, you're in a new center, right? Or
Right. Yeah, exactly.
yeah.
Exactly. So in a sense, you and I, we each have our own bubble. There's a lot of overlap in your and I bubble.
Like 99.9 to the
Right.
million.
But if we go 20 billion light years away from each other, we're going to have slightly different bubbles. There'll be a lot of overlap, almost like a Venn diagram, but not quite, right? And we would see the same Big Bang.
Okay. Well, what if I
Right.
moved, like, say, like
Even if our bubbles
13
aren't
billion light
overlapping.
years?
Right. Yeah, we would see the same Big Bang. Even if our bubbles were completely space-like separated from each other.
No matter how far away we traveled from each other? Or is there a limit to that?
There's theoretical limits. The current inflationary models, they say the seed for the Big Bang is in, how do you say? It's a really strange type of matter, and it has properties that create gravitational fields that are opposite to what we're used to. Normally, when we think of gravity, we think of it pulling or attracting stuff.
But they talk about like repulsive gravity, right?
Right. And inflationary theory takes advantage of the fact that if you have a small amount, only like a few grams of this weird type of matter, then that will be the seed for causing a huge amount of expansion and this repulsive gravity.
Okay. To touch a little bit more on the Big Bang Theory, so that's the beginning of everything we can see. Maybe the beginning of everything, maybe not. It's really impossible to tell.
Right. What's definitely the beginning of everything we can see.
Right.
Right.
And anything anyone else would see, regardless of their place in the system.
Right. Yes. Certainly seems that way.
So I'm going to ask something. I just want to get your reaction to it because it's a question I've heard a lot. I think I think it might be kind of a silly question, but so what happened before that, or what caused the Big Bang?
That's I don't think I can answer that question. I don't know. So we have one of the best ideas that I know of is called Conformal Cyclic Cosmology. It's an idea by Sir Roger Penrose, a Nobel Prize winner for understanding essentially general relativity, gravity, making contributions in gravity. He has this idea for a cosmology where, well, let's back up a little bit. There have been proposed models for a universe where it would expand, 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 and then start, like, it would slow down and then start contracting and then contracting, and then it would crunch, and then that crunch would lead to another big bang. It would like bounce off of it, and then you have another big bang, and then it kind of does that over and over again.
Yeah, and correct me if I'm wrong. The idea behind that is you're in the dense state, you have the repulsive gravity, you expand, but eventually you start kind of losing that momentum, and then gravity sort of pulls things back together into this. Is that sort of the
Right.
the
Yeah,
idea?
something like that. Yeah, eventually the gravity takes over, and then it starts all coming back together. Those were some early models of the universe before we knew about the accelerated expansion. Um, Now we know that if the accelerated expansion continues, gravity will not be able to pull the universe back. And
So
so,
we're looking out and we were expecting things to sort of stop, be slowing down and maybe
yeah,
starting to come back soon, but
right,
they're just going faster and faster and faster, and
right.
it's
We knew at one point that, well, once when Hubble made his observations, we knew that the universe was expanding. We knew that stuff was flying away from us, essentially. Um, and before we knew exact details, um, you could imagine that eventually, if stuff is flying away from each other, gravity is just going to take over at some point, and it's just going to bring it all back together. Um, and recent observations in the 90s showed us that probably if it continues the way it is, it's just not going to happen because it's accelerating and its expansion. It's not slowing down.
because gravity is kind of weak and constant, whereas there's something else going on that's some other source of energy where it's pushing things apart
Right.
much more than what gravity can pull.
Mm-hmm. Yep. Dark energy is what we attribute. But that idea where the universe kind of goes out and then it collapses into a crunch, and then this causes a new explosion, and it kind of goes out, and then it just does that repeatedly. That was one of the earliest thoughts of what a uh, like a cosmology model might work for a universe. And like I said, we've shown that that couldn't be it. Oh, and I should say, in that kind of model for a universe, um, there really isn't a beginning, right? There's a beginning to like each crunch, but like you can imagine that it just kind of like infinitely cycles or something like that.
That does draw like a sort of strange thing in my head. Would you say that it goes infinitely in both directions, or
Probably.
was there some absolute beginning and then it's just infinite from there?
I think the models assume just infinite.
In both directions.
Probably, yeah. Because there's not really a reason to think otherwise.
Well, it's difficult, like thinking logically of how something could be actually infinite in reality in the past and the present. For example, I can imagine starting from one and then just counting up infinitely. Like
Hmm.
that's obviously you would never finish, but that
Right,
process makes sense to me. But
right,
to say that I'm going to simultaneously count from one to infinity and one to negative infinity, that
right. Well, it's like trying to count from negative infinity to infinity. Like you don't, there's not really even a starting point. Like you can't start at negative infinity because anytime you try to get closer to infinity, you've not moved at all.
Right.
if that makes any sense.
So, well, that's the thing. It doesn't make any sense to me, and I'm not. It doesn't necessarily
Well,
have to
it's
make sense to me.
unintuitive, right?
Yeah,
Yeah.
it's very unintuitive. But you're saying like the math sort of implies that that's possible.
You see, that's an interesting question. The math doesn't really well, in that particular model where it like has this crunch and then it goes
Right. Yeah, I get the problems with that because of expansion and stuff, but just the logic of infinite in the past.
yeah, I see what you're saying, but the math for that model doesn't really like it doesn't say like there's a t equals 0. It's just as time goes, you just get this pattern uh of expansion and contraction, and there's not really it's arbitrary. Whatever you could call t equals 0, whatever you want, and extrapolate infinitely far both forwards and backwards. And that's what the math says. It doesn't. It allows for it to be infinite in any way.
I see. So it's like a mathematical description of the process, and you can imagine it going infinite both ways, but the description of the process doesn't necessarily justify that you have a beginning or an infinite or anything like that.
You can plug in arbitrarily large numbers for your time.
Gotcha.
And you can plug in like arbitrarily large in both negative and positive directions. Like you could just add another year or whatever and see what happens. And you could always do that.
Right. So we're not really in a position at all to know whether it's infinite in the past or infinite or anything like that. Like that's just something we have to sort of speculate on, or is there a way to build models and figure that out? Or
yeah, it's really hard to know if the universe is infinite.
yeah.
That's a good observation. If we think like experimentally, you can't test infinity, right?
In any way, yeah.
Yeah, it's not possible.
Even though that I even use the language like I could imagine counting up infinitely. Even I say I can imagine that because I don't even know if that's actually possible. I mean, it's kind of impossible, right? Because you actually couldn't count infinitely. At some point you would have to stop.
You would need infinite time to do it. But we can imagine that you can just like always add another number.
Right, there's no
That's
like
the intuitive
contradiction in logic that you'd have to stop eventually that we know of.
Right. You could just keep going.
At the same time, it's of course this is getting really weird and speculative. I could imagine like that there's a number you get to and you can't count higher than that for some reason. I don't know. Right. There's some physical law where it's like if we were in a simulation, for example, you might expect to find some sort of upper limit like that.
Yeah, that would make sense because they could only compute like so much.
Right. Which is one of the reasons I don't think we're in a simulation.
Right. Right. Yeah. I mean, that's at least one.
Okay. Anyway, you could reel us back. Where
were we? Okay. So yeah. So those type of models, you can extrapolate infinitely far. And so what do you make of that is, I guess, subjective. But this cosmology that I was going to talk about, this conformal cyclic cosmology, it's cyclic in a different way. Instead of expanding and then slowing down and then coming back in contraction, it takes our observations of an accelerated expanding universe seriously. It puts them into the model, and you just have a universe that expands constantly forever and always and accelerates in expansion. And the idea behind this one is in order to measure, say, distance, right, you need a clock of some sorts. And matter is what we use for clocks, because matter has a frequency associated to it, and it's periodic in time, and that's what we can use.
So it's because space and time are interwoven into like one thing. You can't meet someone at a place without also meeting them at the time. You have to have both.
Yeah, you have to have all those. Yeah, all four coordinates. But to measure the time specifically, we use matter typically. Something that's periodic in nature and that we trust is probably exactly periodic.
I can't imagine any way of measuring time that wouldn't involve matter.
Right. But what's interesting about this is, so in the very, very late stages of our universe, when everything is really far away from each other and we've reached this thermal equilibrium spot, there's not really any matter there for the universe to keep track of how old it is.
What do you
And
mean
this
by
is, yes, this is the really mind-bendy part. I don't fully understand it in its full context. It's a hard theory to understand. But what he's trying to claim is that you can expand, you can have a universe that expands constantly and forever and expands, and then you get to a point where the universe loses track of its size, and there becomes a point where there's not a difference between expanded out infinitely large. You go out infinitely large, and then you somehow end up at a new Big Bang from that. Because the early universe has the same problem. It can't keep track of size because we don't have any uh, we have no ways to measure time and or distance in the very, very early universe.
when everything's
So
like in a singularity?
right, the singularity is essentially the same as an infinitely expanded universe.
Because it's infinitely dense.
Right. There's no way to keep track of how the size of it. That doesn't really have meaning in either one of the pictures. And I think Sir Roger Penrose is trying to make the claim that perhaps expanding infinitely far out, and as weird as and mind-bending as this is, expanding infinitely far out somehow gets you to a singularity that explains our universe. And that singularity will have its own Big Bang, and it'll expand infinitely far out. And it's cyclic in that you keep expanding infinite, and you just constantly keep expanding, but you end up with new Big Bangs, like and he calls them epochs at the end of each epoch, right?
Okay, I think I am getting what you're saying to some degree, at least. So to use an analogy, so we've talked before. I don't know if we've actually talked about this on the podcast, but we talked about it before many times. How the difference between momentum, if you're like stationary and moving at constant velocity. If you're on a train, for example, and you're traveling at a constant speed of 70 miles an hour, you can look at it as you're moving 70 miles an hour across the Earth, but you could also look at it as the Earth is actually stable and moving 70 miles per hour like underneath you, and you're actually still. And the mathematics works out, so those are actually the same thing. There is actually no difference if you're traveling at a constant speed. And if we were in space and we were moving at a certain speed across from each other and there was no relative things to measure, we actually couldn't know for sure which one of us was actually moving. Or in fact, we would both be right from our perspective that the other was moving.
Right. The physics would model it the exact same.
So in some sort of analogy, maybe we're also saying that the early universe, because it's infinitely dense and there's no way to tell time, because you can't tell time if everything is the same. You have to have some sort of like change in matter happening.
Yeah, you need that cycle.
And so in the same sense, when things are infinitely expanded away from each other, there's no way, everything is the same. There's no way to tell. And in some sense, these two are equivalent in a similar way. Is that a good way of...
Yeah, that's what he's saying. He's saying there's an equivalency there. Right. The universe in both instances has lost track of how big it is. He has it's like a circle, and in the middle of the circle there's like a ring of angels, and then as you go towards the edge of the circle, you like copy the angels and they get smaller, and then as you go towards the outer ring they get smaller and smaller and smaller, and you can imagine that you can create an infinite number of rings of angels as you go towards the boundary of the circle. You can do that infinitely, and then the boundary of the circle is infinity. And in that case, you've contained infinity within a circle or something like that. And then he uses that idea to make this model where you can imagine you have an infinitely expanding universe, but we're able to write that down and model it in such a way that I don't even know how to explain it, man. It's so confusing.
Well, I think I'm following to
Right.
some extent. That is very interesting. Infinity gets really weird when we're actually trying to talk about it and use it. It's
Right. So what he's so the Big Bang theory, like our current model, like I said, it's just an observational theory. We just looked out and then we wrote down what we saw. It does not make an account for like why that's the case, right?
I mean science really doesn't operate in that axis in general, right?
This conformal cyclic cosmology model is trying to get to the heart of that question, at least attempt to answer the why question. And some of the questions, like the fine-tuning problems, like why are our constants such that they are, the constants of nature, such as like gravity or whatever, it pulls at a certain strength, and if it were a little bit stronger or weaker, we probably wouldn't be here. And like the initial conditions for the Big Bang, for all the matter to be exactly how it was, the Big Bang doesn't explain that either. It just kind of like accepts it and then explains what happens from there. And the conformal cyclic cosmology, and I'm sure other models, but I'm not read up on them, they try to give an explanation for the initial conditions, at least.
Right. You can always ask like another why question. You can always, because you could imagine, even if it's like, okay, yeah, we're definitely conformal cyclic cosmology, that's how this works, and you can be like, okay, well, why is that happening?
Yeah, that's why science is a good career.
Yeah, you'll always have another question to work on.
Yeah.
And cosmology is definitely a field where it's like we have a lot of work to do.
Yes, it's very, very young. It's younger even than something like psychology, which is quite a young field itself.
Right. Or biology, which is maybe a few hundred years at best. A couple hundred.
Yeah. So even biology is weathered compared to cosmology science.
Physics had Newton, and then biology had Darwin. We're still waiting on our cosmologist.
Oh, we had like Hubble. That's sort of like what we had.
Well, was Hubble? Would you describe him as working in cosmology, or is he not more of like astronomy?
I would say you could probably call him one of the first cosmologists, just because he was looking at the quote unquote biggest data they had at the time, right? He was essentially looking at what they saw as the universe. That's for sure.
Sort of like the Rosalind Franklin of the DNA project. Like he did like a lot of the early work, even if he's not really the one who put together the cosmology.
Right. Yeah, Hubble couldn't. He just didn't have the data, right?
Right.
But he knew that if you looked at a galaxy, how far away it was correlated to how fast it was moving away from us.
And that sort of got us started on everything.
Right. And, well, that's an interesting observation, too, because before that observation, our models of cosmology just assumed a static and, like, unchanging infinite universe.
Right. We thought that for quite a long time. I think even, like, I could be wrong on this, but I'm pretty sure since Newton, right?
I think even the ancient Greeks postulated just an infinite, unchanging universe.
I remember reading when Newton was doing his like calculations, and he was like, well, why isn't gravity is pulling everything together? And he's just like, I guess God holds all the parts apart so that they don't collapse. And then Einstein, right? Einstein just sort of assumed a static universe. There was something going on there, right, with the cosmological constant.
Mm-hmm. Yes. So when Einstein made his general theory of relativity, you can you can use the general theory of relativity to create and it's what we use nowadays to create our models for a universe. And implicit in the equations is what's called this cosmological constant. And it can take on different values. If the cosmological constant is 0, I think this is right. If it's 0, then
no expansion.
That's the case where you have a static universe that's unchanging. And I think those were his initial assumptions. Well, actually, I take that back because he had to work to make. So I think implicit in general relativity is expansion. Like it's how it works out, and you have to like work to get rid of the expansion.
Yeah, I remember he put it in his equations initially, and then he called it his greatest blunder, right? And then he took it out.
Right, exactly.
And then long after he died, we were like, let's put this back in there.
Right, let's put it back. Yeah. And it's, we don't know exactly. So someone like Sean Carroll would say the cosmological constant is equivalent to dark energy. They're the same thing. But yeah, he initially took it out, and then now we need it back because we know that the universe is in fact not static.
You talked about the fine tuning of the universe. The cosmological constant isn't necessarily one of those figures, right? Because
yes.
it is
any constant.
Well, it's a constant, but it's not one of like the finely tuned ones. Because
all constants are finely tuned.
All of them?
All of them. They're really strange. If you look at so Newton's equation for gravity is G, the constant G times the two masses divided by the radius between them, or the distance between them. That constant G is a very specific, it's like 6.67 blah, 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 blah times 10 to the minus 11, I think it is.
Yeah.
And constants like that, if we think of like the constant for the charge of the electron, like the electron's a charged particle and it has an amount of charge, and that amount of charge is some decimal number, blah, 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 times 10 to the negative, whatever it is. We have those constants. When we think about the cosmological constant, any constant in physics it's some super specific number that makes the equations map onto reality.
Right. Yeah. I think I maybe misspoke. I was saying that not finely tuned for like, say, life, for example, because it's easy to have different amounts of expansion.
Well,
pretty different ones.
Well, not quite, because if the cosmological constant were much bigger than what it is right now, the universe would be flying away from me. Like, the universe would be much different than what it is right now. And if it were less than what it was, we wouldn't have an expanding universe at all, and we would probably see something like a big crunch. And depending on the size of the constant, had it been different, that big crunch could have already happened. So yeah, we definitely do need, and the cosmological constant is unusual even in the realm of unusual values for the constants.
Well, I know
already.
It's incredibly small.
It's really tiny, and especially when we compare it to any of our other constants. Like I said, G is like 10 to the negative 11. The charge of an electron's like, or the mass of an electron is like 10 to the minus 31 or something like that. And Planck's constant is like 10 to the minus 42 or something like that. So pretty decent. But like the cosmological constant is on the order of 10 to the minus 120. So it's just small. Like, it's so far beyond any other like number we've used in physics. It has a really strange value. It's incredibly close to zero.
So we have all these seemingly arbitrary numbers for different sizes of things and constants, and we can imagine, at least in our heads, that they could be different. You could imagine like the charge of electrons a little bit higher or something like that.
Yeah, exactly.
So how do you think about that? How do you reconcile that?
I'm quite open to the anthropic principle explanation. Just the idea that perhaps the universe, and now I mean like big U universe, all of reality. Perhaps there are regions where those constants are different, and we live in a place where the constants are such that they are, because though like the constants we have allow for us to exist.
Right. Yeah, the anthropic
Right.
principle is we're here, so of course things are such that we can be here. And if you postulate like that, you have all these different types where you have different constants in different universes, smaller, not everything, but
Mhm.
and those ones just fall apart immediately because they don't have the right constants. But of course, we're not in
Yeah.
those ones.
Yeah. Or something, yeah, something definitely different happens that's not creating us.
Well, you could even imagine, like, say, in your this cyclical idea that every time you start a new cycle, maybe the constants are different. But if it's infinite, of course, there are eventually going to be some where like the universe lasts this long and has these qualities.
Mm-hmm. Right. Yeah, so the totality of all reality. I'm most open to the idea that everything that can exist does somewhere.
With the appropriate probability.
Well, I mean with like 100% probability.
Like anything that can happen does happen, is what you're
Right.
saying.
Or has happened or something like that.
Right.
I'm
Well, it
open I'm
does,
open to
has.
that.
I mean, when you're talking about like relative time scales, it's
Right.
like, what do those
Right. Well,
even mean?
I'm talking about like universes that even don't have time or something like that. You can imagine like completely illogical universes to us. I'm open to the idea that the totality of reality is much more than I could possibly speculate.
Yeah, I think.
But a more conservative picture would be like reality will almost always just look like our universe or something like that.
Like it can only be one way. They are this way because that's just how it is.
Right.
Like,
Yeah. I mean, I'm not completely close to that. I
right.
just have a smaller, what do you say, Bayesian prior.
No, yeah, that both of those make sense to me. It's like, well, just because you can imagine that they could be different doesn't mean that they are. You know, some
Right.
things
Yeah.
you that's just what they are, and that's how things are. You know.
Yeah. Um.
But we have this like intuition that we have to keep asking why. Well, why? Well, why?
Yep. We have to keep going. That's a very human thing. Yeah.
And both of them seem quite plausible to me. It seems plausible that it could that's just how it is, and that's where the questions stop. Or yeah, maybe there are these infinite amount of universes, and yeah, they both work for me.
Yeah. I'm quite open to both of them as well. Because you do at some point need brute facts, like like
Yeah,
you
we
need
talked
something
about
that's
this a bit
at
on our
bottom.
like morality. Like you do have to just sort of pull yourself up by your bootstraps at some point, you know?
Right. Yeah. Yeah. Like the numbers exist. Like we don't have to come up with a mechanism for the numbers to exist. We just like the numbers exist and that's at bottom.
Well, especially when you're talking about cosmology, because you're talking about the whole picture, everything. So it's like once you have
Right.
a description of that, you're kind of done. Uh,
Right. Yeah, I could say that. Like it seems like once you've described everything you can see, essentially, it seems like
like
seems like you've
you
done
have a
it.
cosmological model that fits the data and explains
Right.
everything and makes perfect predictions. It's like, oh,
Yeah.
there's no
What's
more
next?
why to really get from there, you know?
Hmm. Well, you could just say like, why this model? Like,
But with that
like,
question, like, I get that you could like say that
like,
question, but like,
does it have an answer? Is it
does it
different?
is it even
Right.
a real question? Like, is it
Right.
more like asking like what color is a cosmological constant or something like that? You know, like,
What
wow.
shape is marriage?
Right?
Yeah.
Yeah. I don't know if that actually makes sense. It's tricky. I think our language is really poorly built to talk about these things in a lot of ways.
The idea of infinity is already like that's already
Yeah.
quite weird.
Oh yeah. I often will think about. I love probability and statistics, and when you start throwing infinities, it's really weird. I came across a thought experiment the other day where you have two doors. One of them has an infinite amount of pleasure in it, and the other one has a 10% chance at getting an infinite amount of pleasure in it. Now, when you do basic probability analysis, you multiply the odds times the expected outcome. But with infinity, the 10% chance to get infinite is the same as 100% chance to get infinite. And so if you're being proper and mathematical about this, it's like these doors are of equal value, even though I have a strong intuition that the certainty is better, but there's no mathematical justification for that. And that's bizarre.
Yeah, infinity is really weird. I definitely agree with that. It's like zero too. Like zero is a little bit easier for us to get our mind around. But I think it's still in that weird kind of abstract space of we can't really think of zero in the same way that we can't really think of infinity.
I completely agree, but I think our language handles the concept of zero better than it handles the concept of infinity, the way we talk about it. I read a book not too long ago, and I wish I could remember what it was, but they were like, imagine if instead of saying there are zero people in this room or there's no one in this room, imagine if our language was such that the only way to say that was like, there's Mr. Nobody in this room.
Oh, right. Yeah, this was the Jordan Peterson podcast.
Oh, yeah. Oh, my gosh. Well, it was from a book, though. It was from a book.
Well, it was probably from Sam Harris's... Sam Harris was saying it, so it was probably one of his books, his maybe Waking Up. So if you say Mr. Nobody, if you say there's Mr. Nobody in the room, there's something over and above the nobody that's in the room, right?
Yeah, like and if you look at the definitions and you talk about it logically, it's like you're talking about the same thing, but it makes it much harder to really think about.
Yeah.
Who's the Mr.?
Right, that's exactly true.
And I think that's part of our problem with infinity, not in a perfect analogy, but in a similar way where we don't have a good way of really describing this stuff.
Yeah. So at least in like calculus, it's kind of interesting. In calculus, whenever we look at like limits or something, we don't. The professors are usually very careful about using the word infinity. They say something like, let x get very big, or something like that. Like, x, what happens when x gets large? They never quite say, let x go to infinity. We can say the limit as x approaches infinity, but the way to think about that is what happens as x gets large.
Right. Our minds just aren't really built to understand that, so I would understand trying to avoid using those terms until like maybe you understand the math and then you sort of know. It's sort of like how like biologists will talk about like purpose of different things.
Right. Put like a teleology on it.
Right. But it only is useful in the context of people who understand that you're not talking about it in a different way,
Yeah, exactly.
That's an interesting thing.
Well, even in infinity, we've shown mathematically that different types of infinity exist. And we have proofs for that, which is, I think, is fascinating. Like, whenever we think of infinity, you're just like, it doesn't end. Right, like, there you go.
I really can't conceptualize it at all.
Yeah. Well, I mean, I feel like you sort of can. You can imagine, like, not ending or something. Like, that's a pretty good intuition of just like it. If you think of a number line, we can imagine that there is no end to that number line, right? I feel like that's somewhat
I can say that and I can agree to that, but whenever I actually like sit there and think, okay, what would it be like to have a number line that never ended? I'm picturing like a moving number line, but I can't picture it forever. So it's like, is it really an infinite number line that I'm picturing? I don't know.
Right. I see what you're saying. I would think so.
Yeah, but I think we can get close.
Just that it's strange to me that we've been able to show that different types of infinity exist. You would think if you imagine just never ending, how do you get more than that, right? More than never ending.
But bigger and smaller infinities and such.
Well, and this is what's interesting, there is a smallest infinity, right? And that's the counting numbers. Like 1 to infinity, that's the smallest one.
Are there more counting numbers or are there more even numbers?
Those are the same.
Yeah.
Right. Yeah, they have the same. So there's the same number of counting number, odd numbers, even numbers, numbers that divide by 5, like numbers that divide by 2. There's the same number of prime numbers. But if we think of the real numbers, so not just 0, 1, 2, but between 0 and 1, there's a half and a quarter and any irrational number you can imagine. That infinity is much, much bigger than the counting numbers or the even numbers.
Which is weird because it's almost intuitionally it's like the opposite of what you would think. Like, of course, there's fewer infinities between the 1 and the 0 than there are between 0 and infinity.
The amount of numbers between 0 and 1 is more than the counting numbers.
But what can more even really mean when we're talking about infinity?
In this case, it means that we can pair up if you try to pair up the numbers 1 to 1, like we start at 0, we match it to 0, and then like we go to 0.00000001 and we match that to 1, and then we do 0.00000002 and we match that to 2, and then we just keep matching it over and over again. You can show that essentially you'll run out of counting numbers before you've matched up all the numbers between 0 and 1.
So like if you graph them, the one infinity approaches infinity faster than the other one.
Infinitely quicker.
Infinitely quick.
Yeah, right. Yeah. Like you literally cannot match 1 to 1. And I say between 0 and 1, but you can imagine any interval.
Right, like between numbers, 0 and 0.5.
Any two numbers that are not equal.
Right. Between 0 and 0.01.
Between 0 and 0.0 with a googolplex of zeros, 0.1. Between 0 and that number that's insanely close to 0, there are more numbers than there are counting numbers.
That is incredible.
Yes, it's very quite strange. We use Cantor's proof. Cantor's proof is interesting because it's not like super mathematically like detailed, and it doesn't take like a ton of, you don't need any mathematical background to explain or to understand the proof. I can explain it right now. So what he did is he imagined that you could list out all of the real numbers. Like he just imagine, just have a list. That's all the real ones, and it's this infinitely long list. What he did is he took the first number from the first number on your list. So the first digit of the first number on your list. If it's a 1, he changes it to a 0, and if it's anything else, he turns it to a 1. So for the first number and the first digit, if it's a 1, he changes it to a 0 and 1 otherwise. For the second number, he takes the second digit and does the same thing. And for the third number, he takes the third digit and does the same thing. And he does this, he goes all the way down the list, and he's created a new number that wasn't on your list because it's different from the first number in the first position. It's different from the second number in the second position, the third number in the third position, and so on. And so we've assumed that we've listed all of the real numbers, but then he showed that you can,
a new number.
Then he showed that you can always add another one. Yep. Even though your initial assumption is that you have already listed them. And so it's a proof by contradiction is what it is.
Wow.
He shows that your initial assumption doesn't hold. Yep. You can contradict yourself.
And that's like a really true case of just logic really trumping intuition in a very clear way that even once you understand it, I don't know if you can really accept it. I mean, you can accept it, like you can say that and you can know it, but can you really think that? I don't know.
Yeah, I think you can.
Have you worn away that intuition? You think?
I've accepted it. Yeah.
Okay.
Well, especially okay. Now we're a little off topic, but it's fine.
It's useful to understand things like infinity for this, I think.
Trying to do a physics degree
Yeah.
has taught me that your intuitions will definitely be pushed and pulled and warped and changed, and you're able to build new intuitions where you previously would have thought that's just you couldn't ever possibly get there, right? Something like I think a good example of this is something like four dimensions. I think, like, in my mind, I have a good intuition of what four dimensions is.
Yeah, I think
and stuff. And I think that wasn't always the case. I think at some point it was hard for me to kind of imagine four dimensions. And now I would go so far as to say I'm really comfortable with it. It's not weird. It is weird to me, I think, because I think most things in the universe are weird, but like it's not outside my intuition like it used to be.
Yeah, well, you can build new intuitions and you can have thought experiments, which I think I've mentioned this before, but Dan Dennett, he'll call good thought experiments intuition pumps because they'll sort of like pump intuitions you have. Mm-hmm. And I think a good one for like four dimensions is like the idea of moving from a 2-dimension to a 3-dimension, and you can watch that, you can see that, and you can sort of internalize that, and that'll pump your 4D intuition in a lot of ways. And there's some other things.
And especially when you start messing with like vector spaces and stuff of that sorts, and linear algebra, matrices, and what have you, you start learning about in dimensions, right? So like any arbitrary number of dimensions you want. And in physics, we tend to use 4 because that's
that's what we observe. We're working with.
Yeah. Although you can imagine like higher dimensional mathematical objects that we use in physics, but like, as far as the universe is concerned, it seems like we're in some 4-dimensional space.
Well, that's really the beauty of the math, is the math just, it doesn't care about any intuition at all, and it just operates according to the rules, and it's a language of talking about these things that is free from any of these like language problems we've talked about before.
Yeah, it doesn't have that baggage.
Right.
And it's interesting because then I'm taking a class called Introduction to Abstract Mathematics this semester. And we've gone over this semester, it's all been propositional logic. Trying to think of like logical connectives like and, or like implication like A implies B. And in our last homework, we were having to write the converse and contrapositive of some sentences. And so you could say something like, if this hockey team wins the championship, then pigs can fly. You can write the converse of that, which was to say, if pigs can fly, then this hockey team is going to be the best hockey team. And he gave us a few of these examples, and on the last example he gave us, he said, if you want to do well in your math class, then you need to do your homework. And he put that in there specifically because whenever you try to do the contrapositive of that, the words want and need they don't really make sense like mathematically whenever you're trying to like show the logical opposite essentially of that. It's like if you need to do your homework, you want to pass the class, or like if you want to do your homework, you need to pass the class. Or it's hard to say the opposite of that because like language has just that baggage to it. Yeah. And that's the exact reason why he put that on the homework, is to show that in English, and I'm sure any other language, like it has that sort of baggage to it. Whereas in math, it really tries to cut all of that out.
Right. You can say if P, then Q, and then you could say if Q, then P.
Right. Or if not Q, then not P.
Right. And that's...
Right. And that makes perfect sense.
Right. But whenever you throw in all these extra words, which have...
Yeah. Want and need and... all those kind of weird
and stuff. All these words, we have like lots of understanding of them that we're not really aware
Hmm.
of on the surface necessarily.
Yep, exactly.
That's why math
You,
is awesome.
most people know a lot more than they might think.
Oh
Like,
yeah. Well,
it's like,
you'll never realize that more than whenever you're teaching someone. I used to play online games a lot with people who spoke other languages, and I'd help them like go through English, and they'll ask me
mhm.
something, and I'll have to sit there and have to think like, how do I know
Yeah,
that that's what that is? I don't. That's just how it is.
yep,
But
that's just how
I
it is, right?
don't know the
It's
rules, but I know that's right, and that's weird. So to bring things back, so I
okay,
think that it was actually useful in a lot of ways because I mean math and infinity, like these are all crucial for cosmology.
right, exactly. Oh, and since we're on this,
Yeah.
this is an idea that I've been running through lately. And so, if we are using mathematics to model physics and to model our universe, and we at least we assume that the number line is infinite, right?
Hmm. Yeah.
I don't know how to like formalize this, but my thought is perhaps that's a way for understanding that the universe could be infinite. There's some sort of connection between the math and then the universe in which the math is embedded or something like that. If we have this infinite structure, yeah, this it's a hard idea. I haven't like talked to anybody about this or tried to say it out loud, so it's hard to get out there. But like the idea that in math we have like infinite number lines and infinities and such, but those are within the universe, right? Like we could write we are embedded in the universe. It makes me think that the way for that to be possible, if the universe itself was like infinite, right?
I think there's a good way to get into that, but I think first, would you say surely you can postulate mathematical things that definitely can't exist, right? But the math works perfectly and you can use it.
like don't exist, like non, like what do you mean by that? Because there's certainly like, let's say like abstract algebra. I'm
Well,
working
I
with a
could talk
tutor right
about
now, and
we'll get more into this, but let's just talk about Boltzmann Brains for a second. It's the idea
okay,
that you can have these in the certain kinds of universes, you can have fluctuations and you might randomly assemble like a fully conscious brain.
right.
Now, I know there are some cosmologists who say that these just aren't even possible at all in principle, but you can
Hmm.
actually do the math and show how they could be possible given certain mathematical parameters. So, is that not an example of something that could potentially be like mathematically possible but not possible in our universe?
I see what you're saying, and I think the answer to that is yes, but it's so I see what you're saying.
Hmm.
The idea I'm trying to get at is it's slightly adjacent to that. Uh,
Okay.
it's it's the idea that like no, I see what you're saying. It's like hmm, yeah, that's a hard one.
Well, I feel like you're saying something like because we use infinity in math and it clearly works and there's clearly like relationships between math and the world, therefore the world might be infinite, right? Is that not?
Yeah, something like that. There's a connection between the infinite, like the fact that we're able to write down and think of and talk about infinity. This idea of never ending. Um, it makes sense to me. Um, that the reason we're able to do that is because the universe itself is actually infinite.
So then like we can use this or a different example, but like because we can write down and talk about Boltzmann brains, for example, and
Right.
therefore there
Right.
must be Boltzmann brains out there in some sense.
Something like that. Yeah, that wouldn't be far off. Yeah, we're really close. And this is close to my, like what I was saying earlier. whenever I think of like the totality of reality, what
Hmm.
like not just the universe or the observable universe or even like the multiverse or something crazy like that.
Right.
Like all of everything everywhere. Like
At
that
all
to
times.
me, yeah, at all times or at no times or at just like
Yeah.
the totality of anything that can or cannot be. There's just like literally everything.
Yeah.
That to me um is probably infinite. I don't like I can't come up with a reason for that to be with a bound.
Well, I think I get why you probably get there, and that's I think. So you would you describe yourself as someone, I know the answer to this, but for everyone else, would you describe yourself as someone who thinks that we invent math to describe the world, or we actually discover the math as we explore the world?
Um yeah, that's a good question. I'm unsure. I really am unsure on that question. It seems to me that we're discovering math. It doesn't seem to me that we're inventing it.
And in which case, if you did have the intuition that we were discovering it, that would make sense
Mhm.
that you would also infer that like infinities exist. Whereas if you thought it was something we sort of invented to describe things, then you could also imagine that we invented infinities, you know. So I think that really gets at the
Yeah. Yeah, I see what you're saying. That makes sense.
it's an interesting question, and I do find that I mean there a lot of people have different intuitions on this, but I
Hmm.
do notice one thing I do notice, even though my intuition is the invention, I do notice that the more people seem to learn about math, the more they get pulled to the discovery end of things. So that's
Right.
not proof of
Yeah.
anything, but it is an interesting observation.
Well, I mean, on so Sean Carroll, physicist that in America, very mathematically inclined, knowledgeable of math and physics, obviously. He tends to think that we invent.
Yeah, there's no definite like
Yeah.
answer, but there are smart people on both sides who think both things. But you could say that about a lot of things too.
Yeah.
So
But I definitely, as I, like you said, as I learn more math, it does seem to me that I'm not inventing something.
right.
It definitely seems like I'm discovering something that was like already there or perhaps hidden.
Well, I just look at the math as like the language you're using to. It's a language we've invented to describe the real stuff. And like the stuff is real and the relationships between the stuff is real, but the math is sort of just
Right.
the way we
Well,
describe it.
yeah. And that's interesting to me too, because like if that's the case, and the universe is, let's say, not infinite,
Hmm.
why do we have infinity? Like
Well,
if we've invented it.
it's just like the product of our intuitions about things and trying out different things and it's like we because it goes back to this thing where it's like because we can think of something we sort of we want to imagine it, so like the universe thing, so it's like we imagine all these because we can imagine the universe in a different way, we imagine different universes where things are a different way. And that could just be a product of our imagination. And if infinity doesn't exist, then I think you could make a reasonable case that it is a product of our ability to imagine that things could
Right.
just keep
Just
going.
not ending.
And then we find a way to describe that with math. And it honestly could go either way. And it's more of a. There are ways you could figure this out, I guess. If you could actually experimentally, I don't know how you could, but if you could experimentally prove that there are infinities or that there's an ultimate cap of how high a number can be.
Right. Something like that. That would be an interesting experiment.
I feel like due to the nature of infinity, the only way you could prove that is to prove the opposite. So you could get to the highest number, maybe. That's, but you could
If you could
never
show,
get to
yeah, if you could
infinity.
show there's a highest number, that would be very surprising.
That would be
Yeah.
shocking.
Yes. That would break a lot of math, actually. It would break calculus
Well, it
because you
would be an
couldn't do
incredibly big
limits.
number, right? It would, yeah,
Yeah.
calculus would need to be reworked.
Yep. Because at bottom we assume differential, like smooth and continuous differentiable. You can like
Right.
You can break up a line into infinitely small pieces.
Well, then you would know factually that math is invented, because that's the only way you could have stuff like that.
Well, would you? Or would you just say what we understood about it was wrong?
Well, you would say like, oh, well, we made up all this infinity calculus stuff, but clearly that can't be, because we can't have infinity.
Oh, I see what you're saying. Yeah. Yeah, yeah. When it comes to infinity, it's really quite strange.
Yeah. All right. Well, we could keep talking about infinity, but let's try to get back to cosmology. I do think it was useful.
Cosmology.
And interesting. Fun. Yeah, oh yeah. So fun. So I guess let's talk about models.
Models. Okay.
So we talked about the cyclic model, the conformal cyclic model you mentioned there.
And that's the mind-bending one where space is essentially always expanding, always. There's the other cyclic model where like stuff expands away from each other, slows down, and crunches back, and then explodes again. It kind of does that. So there's like those two ideas of cyclic models.
And then you have other models, right, that maybe aren't cyclic.
Right. So like the current Big Bang model is not cyclic. So the universe started in some special, very hot, dense state and has been expanding since then and has been accelerating the expansion even. And if we extrapolate that forward, it will just expand forever and then it'll end in some heat death of the universe where everything is just spread out evenly. There's not really anything happening.
Like, what are we looking for and how might we find it? Like, how will we know when we have like the right model? And
well, just when it makes the correct predictions, when it just like overlays, like we look at the data of expansion and it just like it just fits the data, right? So like all the models we have.
What's some of the data? Like, how do we know when the model is good or bad?
Well, currently we don't have we don't know what singularities are, like currently. They're predicted in Einstein's general theory of relativity. That if you have too much matter too close together, it just collapses into a singularity. I don't think we quite understand those.
So you're saying we don't understand like the beginning of the universe. We also don't understand black holes. Is that what you mean when you're saying we don't understand singularities?
Yeah, exactly. Okay. We definitely don't understand. Like, so we have the Big Bang, and then what happens is like, how do I say this? Like, from time equals 0 to how do you say, to like time equals 10 to the negative like 42 seconds or 43 seconds, we have zero idea of what's happening there. Like it just,
because all our math breaks down.
Yeah, the matter densities are just too high. And in my mind, I don't know why the very beginning, the very early universe itself did not collapse into a black hole. That doesn't, I haven't found an explanation for that because they say it's a singularity. Cosmologists, they say it started out as a singularity. Singularities are the things in black holes, right? Like why is the universe able to...
Why is there no repulsive gravity in black holes?
Right. Yeah, it's just like if the universe if all this matter was really all this close together and stuff, like how was it able to expand? Like that's a question that I don't quite understand myself.
Yeah, I think there is a good answer to it, but it is, I think, beyond us at the moment.
Right. So inflationary theory purports to explain that. They just say this repulsive gravity type, this material that creates repulsive gravity just allows for everything to be pushed away, I guess, before it collapses into a black hole.
I know general relativity predicts repulsive gravity. Like, that was something Einstein was thinking of before.
Right. Yeah. Whenever you're thinking of what general relativity is explaining, Einstein's equation says that matter equals gravitational field, essentially. Like, energy that's the equation. Mass. No, it's just like,
Right.
well, yeah, just like on one side of the equation you have matter and energy,
Right.
and on the other side of the equation you have gravitational field. So it's like matter and energy equals the field,
They
and
are
like
the
that's
same.
yeah, yeah. That's what general relativity is saying. And this field, you can imagine it being repulsive or attractive. In both, they both work out mathematically. But it just so turns out whenever you go outside, the Earth is pulling you down, not pushing you away. And I don't know this type of matter that they talk about. They said you only need like 2 grams or something like that in order to get the expansion rate of the universe to be what it is and what it was.
Mm-hmm.
Even if that's true, we don't have the initial conditions for those 2 grams. It's just like,
Yeah, like where did those come
like,
from?
yeah, where did that come from? It's just like they purport to have this explanation, but then it just seems like you can always keep going with it. It doesn't.
There's another weird thing there. Even just like the question I just said, like where does that come from? That sort of implies causation and time and things like that, where it's like if we're talking about the initial conditions of the universe, we don't necessarily have time. So it's like, where did that come from? That's like there was nothing and now there's something, but like
right.
that there's no time for that kind of causation to happen.
Exactly.
So it's like there's another place where language is, it's really hard to talk about this even.
And also, what I'm unsure of, and I haven't been able to figure this one out either, it seems as if space was already there, and then like something happened in space, and then it seems like other people claim that like space was made at the Big Bang.
I've
But that
always
isn't-
understood as that like space and time began at the Big Bang, at least as far as we know it.
Right. Yeah, I'm unsure. I'm unsure of that myself. I don't know.
Maybe like there is already space time, or maybe there was just space with no time, then the time got injected or something, or what do you mean?
Or yeah, just the structure of space time was just like always there. That that
And
seems
there was just no
somewhat
stuff in it?
reasonable. Yeah. Or there was stuff in it at different spots, or
Well, at some point you have to have stuff unless you're just postulating an infinite past as well.
yeah. Well, I mean that seems reasonable to me. That's the thing.
So maybe like space time is just a given brute fact. There's space time everywhere, and
And stuff happens
changes.
in it
Stuff
periodically.
happens. Stuff happens all the time in all times.
Yeah.
Interesting.
Because like it seems like the inflationary model has space before you have this matter stuff.
Right. Well,
Like,
like it's
you have
how
to-
do you expand without space to expand into? Well, unless the
Right.
space.
Well, you
itself
don't have
is
to expand
expanding.
into the space. Yeah, I'm okay with that. Like the like it's expanding. What's it expanding into? What like the stuff between you and your monitor, right?
Yeah.
Not the air,
Not the air. The
but like
space itself.
that space. Yeah,
Like, we imagine as a
that's
vacuum.
what. Yeah, that's what space is expanding into.
Well, is that? How can you say space is expanding into that? Because that is space,
Right. Exactly.
and
Yeah.
space is just expanding into
That.
nothing. Well, not even
That
that, because
other
that's
space,
space.
yeah.
Space isn't expanding into space. That doesn't
Yeah.
make sense.
Yeah, we can't think of it as embedded in something else.
Right.
Right. That's where the problem will be. If we try to imagine like so the problem is we can imagine being outside of the universe, kind of like looking in, sort of like a God's eye view or something like that.
We can imagine it, but whenever you get
But
logical about
yeah,
it, it's
but you shouldn't. I don't think you should think of it that way. You should think of it like as a thing in and of itself, right? That you can't really look at from the outside.
yeah. I mean, where would you be if you were looking at the universe from outside the universe? There's nowhere for you to stand inside
Yeah.
the universe to be outside of the universe.
Yeah, yeah. If I say the universe is expanding into nothing, what is that? How do you make sense of
What
that?
is nothing? Well, that's a problem with the concept of nothing. I don't think we're really capable of thinking about it.
Right. So we
Um,
say so the universe is expanding. Like that's pretty. But so this is interesting too. What we mean when we say the universe is expanding is that everything in the universe is moving away from each other.
right.
We haven't actually measured space and see that as like we don't have like an experiment that shows space is expanding. All we know is everything is seems to be moving away from each other.
Right. So you could imagine that. I don't know.
Yeah, I
um,
don't I don't know either. Yep.
well,
So
isn't the idea behind dark energy is that it is causing space itself to expand, not just the stuff in space, but space.
so dark energy, how I understand it, is the energy of space itself. So like we used to think if we go to like intergalactic space where there's no atoms or no matter or anything and you just have like this cube of emptiness.
A vacuum with no matter or
No
radiation or anything.
nothing in it, anything like that, right? No photons, no radiation going through it. It's like a box of nothing in its truest sense. Um
As far as we can like picture nothing anyway.
So that empty cube box is actually not empty. There's an energy to it, a very tiny amount of energy, and it's just the fact that you don't have nothing there. You have space there, and space fluctuates and has properties and stuff. What was I getting from this? Where was I going with
Well,
that? I already forget.
I think you were initially suggesting that that might have always been there, that nothing with some energy left.
Oh, okay. I see where we go. Okay, so we're out in intergalactic space. There's no radiation. There's no matter. There's no particles, and we have this like box, this cube of nothingness, right?
Mm-hmm.
Um, we now know that that nothingness actually has energy in it. Even if you don't have particles there or radiation or anything, there's still some amount of energy there. And it's just the energy of space itself. It just intrinsically has energy. And if that's what dark energy is, then as the universe expands, you get more space. So you have more dark energy, which causes it to expand even more, which gives you more space, giving you more energy to keep pushing
Right. And that's why
outwards.
it's accelerating.
And yeah, and that's why it's accelerating. Although, if you look at any individual cube of space, the energy is constant. Like for that cube, it's a constant amount of energy, but because it's expanding, you're getting
More
more
cubes.
space. Yeah, you're getting more cubes. And so dark energy is a constant value. It's pushing at a constant rate, but you're getting more of it
Right.
as it goes on.
So we are getting more of it, and in that sense, like it probably wasn't here before because I mean otherwise.
Well, it could have just been always expanding, always. Like, I'm okay with that. Like, it was just always expanding.
Well, at some point well, if you have more now than you used to have, and if you had less even the day before and less even the day before, you do rewind that, and eventually you don't have any space, right?
I'm not sure. Well, not if it was, like, infinitely expanding. Because then you could just, like... Because you can imagine a space that just contracts always. And it's all it does is always contract. And there's no limit to when it'll stop contracting. It'll just like always and forever contract. There's no point where it'll stop.
Yeah, I mean, I can imagine that. Of course, it'd be contracting incredibly slowly.
Well, at any
From our
rate,
perspective, if we were like watching it, for example, like I mean,
yeah, the rate really isn't relevant because if we extrapolate to infinite time, the rate doesn't matter.
but I mean, it's like you're suggesting that maybe space has just been always expanding, and we're just looking at a little slice of it. And it was infinitely expanding before anything else was here, and it's going to keep infinitely expanding after.
Probably. Yeah, that seems reasonable to me.
That's weird.
Yeah. I mean, yeah, any model I'll give you is going to be like I can't think of a model of the universe that wouldn't be.
On the first page on the Astrophysics for people in a hurry, it says that the universe is under no obligation to make sense to you.
Yeah, that's true. Yeah, that's true. And it tends to not make sense a lot of the time. A lot of it does make sense, and then there's always something about it that seems to make no sense.
But in cosmology, we're just trying to take all those things that we do understand and make sense of them in one complete model. And that's really what cosmologists are looking for right now.
Mm-hmm. And I think this is closely tied to, in physics, we have a problem of trying to tie general relativity to quantum mechanics. And the idea is, in general relativity, the structure for that, space is what we call differentiable. It's smooth and continuous. It exists at every point. You can zoom in arbitrarily far. It's smooth, completely smooth and continuous. Whereas our description for matter and energy is different. Like there's not a smooth and continuousness to matter. There's bits of matter. There's pieces of it, right? Atoms are made up of protons and neutrons, and those are made up of quarks and gluons, and like those are the bits that are at bottom, and you can't zoom in anymore unless you're thinking of like string theory or something. Right. But even if you are like thinking of something like string theory, like the string is the bit. Like you don't zoom in any further than that, right? There's always like an end bit, and one of the current problems in physics is that those are two separate descriptions of reality. Quantum mechanics tells us that you cannot actually zoom in arbitrarily far because of quantum mechanical effects, and even general relativity. Like if you try to probe smaller and smaller regions of space-time, you have to use higher and higher energy probing devices, like just like higher energy matter, higher energy light, or something like that.
Eventually, you're gonna have a microscope the size of the universe, and
right. And eventually, you're just gonna have such high energy that you're just gonna make a black hole, and then the region that you were trying to observe is now blocked off by the black hole. So, like quantum mechanics tells you you can't zoom in arbitrarily far, but the structure of general relativity has no qualms with zooming in infinitely far. It's just like it's perfectly okay with that.
So it's possible that in principle you could zoom in infinitely far, but in practice it's with our universe, it's just never going to happen.
Well, if you take just general relativity, just like the framework of general relativity, since space is differentiable, you can zoom in infinitely far. You can ask about specific points in space and like their exact properties and something like that. Whereas like you can't do the same quantum mechanically. Like in quantum mechanics, you can't zoom in arbitrarily far and just keep zooming in. There's this hard limit.
It's amazing how many different topics we end up coming back to this sort of idea of marrying general relativity with our standard model.
Right. And if we're thinking about cosmology, the very early universe has this problem. It's right in our face, right? We don't understand the physics of the matter of the very early universe.
Yeah. So it's like we've talked about some models, and there's lots of speculation and ideas on what was happening at the beginning, but it's like really we don't know. There's just no way to actually know because the equations do just break down, and you can interpret that in a lot of ways, but the real answer is just I don't know.
Well, it's more interesting than they don't necessarily like break down. It's the equations don't talk to each other. They don't like like currently our models of general of gravity don't talk to our models of like the electromagnetic force or the strong nuclear force or weak nuclear force or something. It's
Right.
like we have those forces over there on that book, and you can read about them all you want. And then we have gravity in this book over here. They're completely separate books and they don't talk to each other. And we can't figure out how to make a book that brings them both in, you know?
Yeah, well, it's a bit like having a scale, having two scales, and it's like I take an object and I put it on the scale. It says it's 5 pounds. I put it on this object. It says it's 5 pounds, and I do that with a 1,000 different objects, and they keep agreeing and they keep agreeing. But then I get to this one different object, and I put it on one, and it says 1,000 pounds, and then this one says 1 pound, and it's like, why can't you guys just measure this one object? I don't.
Right. Exactly.
You did all these other ones perfectly.
Yeah. And that's what in GR and like quantum mechanics or quantum field theory, they have both been tested to like ridiculous accuracies. They're both like our best theories of what they're describing. And it's really strange to me that we can't figure out like why don't they work together? It's and it seems as if we're just using different descriptors for them. So it a little bit makes sense to me that they won't come together.
Right. They're both basically heuristics.
Right. But the problem is in the universe, they work together just fine.
Right. Yeah. The universe did happen. The Big Bang did happen.
Yeah.
So
The universe is here and it has space and quantum mechanics both intermingling, and we can describe one or the other. We can't describe one and the other.
Here's another interesting bit of speculation on if mathematics is invented. Perhaps the way our mathematics aren't capable of describing this phenomenon, and we actually need some sort of like higher level, like
something better.
Yeah, something better than math, if you can even imagine something like that.
Or just a better math.
Right. Like if you could imagine hyper intelligent aliens who look at us like we're dogs or something, you know.
Yeah.
Dogs are smart, and you can teach
yeah.
some things to dogs, but they won't understand quantum mechanics, and like they have their own quantum mechanics.
Yeah,
and maybe that explains it. So
it explains something, that's for sure.
But if math is discovered, then there should be an answer here, and I'm optimistic, actually.
Mm-hmm. Yeah, I'm optimistic too. It's also a nice it's a good field to be in right now.
Yeah,
I would say, because it is new and there's some good open questions.
The person who does that, like, they'll answer so many questions.
Yeah, ideally, hopefully, right?
Well, we'll at least have a lot more solid information about like how our universe started.
So at least for like the early universe, when everything was really close together, really high energies, I think it'll be mostly the particle physicists that explain that. Because they're the ones probing, like at the LHC, they're the one probing super high energies. They're the ones looking at that.
They come up with a new idea where it's like, oh, wait, this is like this thing.
Right.
And
I think they'll see something in an experiment and then be like, oh, we can explain something in the early universe from that.
It doesn't necessarily have to be a new experiment, though, you know, because like Einstein, like they knew about the Mercury thing for quite some time before he came up with that idea. So it's like the experiment might have already been done, and we just haven't had the person come up with the right idea about it, you know?
Right.
Look closely enough at it.
We definitely have plenty of experiments that we don't quite. For instance, there's an experiment called the G-2. I think it's a muon experiment.
Oh yeah, that's like last year.
Yeah, it's like last year. So the idea is if you put, I think it's a muon in a certain type of magnetic field, it wobbles. It just like wobbles back, like a spinning top nearing the end of its spinning. It has that wobble to it.
A muon is one of the fundamental particles, by the way, for those who
Yeah,
aren't
yeah.
familiar.
Muon's a fundamental part. It's like an electron, but a little bit heavier,
Right.
essentially. Same amount of charge, just a little bit more mass. Anyways, when you put it into a magnetic field, it has a wobble to it. And our theories predict that that's the case. It should wobble, but the numbers are a little bit off.
and when they say off, we're talking about like the equivalent of saying, oh, it should be 1, 2, 3, 4, 5. Oh, but we actually got point 1, 2, 3, 4, 6. So, oh man.
I think it's 11 decimal points or
Yeah,
something like that.
it's
So yeah,
incredible.
we're off not by much, but like
But that's how much stock we have in the standard model is that like this tiny difference is actually meaningful.
right. Well, I mean, over the last say 100 years, because it's about when quantum mechanics came out, was about 100 years ago. All they've been doing is refining it. Like we've had thousands of physicists, thousands of engineers, and what give you doing instruments and experiments and stuff, trying to like fine tune all these numbers and stuff, and it's been really successful. We can make an account for pretty much everything like in your normal day-to-day life. Like that kind of physics is more or less known,
Oh yeah,
and explained
solved.
really well. But there's still, like I said, those few decimal points are,
Yeah,
and
but
it's
those
like,
might be the key to the early universe, you know.
yeah, and it could be that we just need to tweak the model just here and there, and just keep getting like that extra decimal point, and then eventually we'll get there. But I could also imagine that we just, perhaps there's something more at bottom that we're missing,
Another
and
Einstein
like,
type of discovery where it's
yeah, a
like,
more like a more fundamental type thing, that, and then from this new fundamental idea, like that 11 decimal point just like comes from it, right? It just falls out from it. I could imagine that's the case.
string
But
theory is promising, and I think the prospect of other dimensions is another, like, we could learn so much if we could discover more dimensions. That would, like, maybe dark energy is just like, it's just something that's really obvious, but it's tucked away in another dimension, and so we can't see it, and it's
yeah,
like, that's not actually an empty cube. There's actually a bunch of stuff just 90 degrees between two 90-degree
orthogonal.
points.
Yeah,
Yeah.
orthogonal to it. Yeah. No, I could definitely say that, because if we think of like, if space has extra dimensions more than the four that we know of, what gravity is curvature of space,
Right.
right? And so those extra dimensions are just extra dimensions of space. And so
Right.
like gravity could easily exist in those other dimensions, even
Eke
though
through them.
our matter particles couldn't.
Right.
Like our matter particles are stuck to these four dimensions that we're in right now. But like gravity, since gravity is space itself,
Yeah.
it obviously could penetrate those
Now you
higher
say
dimensions.
the particles are stuck. I think that's true for the most part, but I have seen experiments. There's some particles I know that kind of like leap in and out of existence in some sense. Like they actually will pop in and out.
Yeah, you always, yeah. So by Heisenberg's uncertainty principle, you can create particles for a short amount of time.
Right.
You're allowed to go from nothing to some particles back to nothing in a short amount of time by Heisenberg's uncertainty principle.
But it's like those particles, they have to come from somewhere, you know? Like,
right. Well, that's interesting. They can actually come from nowhere. As long as they exist for a short enough time, you're allowed to literally, the conservation of energy, very famous things of your in system. The amount of energy you have in the beginning is always going to equal the amount of energy you have in the end.
yeah.
Heisenberg's uncertainty principle allows you to violate that for tiny amounts of time.
I did not know that.
Yeah, you can not conserve energy, but only if you do it for a really tiny amount of time. And you can show this too. Whenever an electron, let's say we have like a hydrogen atom, which is a proton and an electron orbiting it, you can add energy to the atom and excite the electron to put it in a higher energy state. And as it drops, and things in our universe tend to like being in a low energy, what we say ground state, just like a low energy state. And so you can excite the electron, and it will just naturally decay into a lower energy state, right? What's interesting is Heisenberg's uncertainty principle, when the electron decays to the lower energy shell, it still has the same energy. It still has the same energy as the excited state before it has released the photon, but it only does that for a teeny tiny amount of time, and then it releases a photon equal to that energy difference. So yeah.
So you would say it's more likely that we can violate the law of conservation of energy for short periods of time than it is that like stuff is like sort of slipping in and out of another dimension.
Yeah, so I think it's true that you definitely can violate conservation of energy.
Gotcha.
For tiny amounts of time. I'm pretty certain of that.
Very nice.
Well, just to end on that just a little bit. If you look at the beginning state and the end state, you will always have the same amount of energy. Like in the end, energy is conserved.
But you violate it like briefly.
But you can violate it ever so briefly. Yep.
In music, we'll do something like that sometimes. Yep. Well, we'll be playing in time, and it's important to stay in time, but you can sort of slow down a little bit at the end of a beat and then speed up just a little bit more on the next beat, and you can do the illusion of time. Mm-hmm. But it's actually the same every time.
Exactly. And so like if you want to create like an electron positron pair, that can exist because electrons are super light. They can exist for a little bit longer, but if you want something to exist, like say a person to pop into existence, that would have to be an extraordinarily tiny amount of time by Heisenberg's uncertainty. Like it's probably not going to happen just because of like
or like a Planck unit of time.
Planck times or something. If that, right. If that. Yeah, so the more energy you borrow, the less time you're allowed to borrow it, essentially.
No, that was good. Thank you. That's. I think we got to wrap it up, even though we got a little bit off topic. I think it was still fun and interesting. Yeah. And I definitely learned something. I always appreciate you sharing your physics information.
It's always fun. And so I'm getting worried. I don't know how to say this, but like I'm taking like a GR class right now and quantum mechanics class right now.
Yeah.
Dude, this stuff is so hard. And it's so like it's beyond me at the moment, and I want to talk about it here on the podcast and stuff. And it's worrying because like I don't know how to talk about it sometimes because it's so abstract and different. And I've had a few years of like math under my belt, and like and it's hard to explain those concepts like in layman's terms.
Right. Well, I imagine it's a good exercise for you. Sort of. So, check your own understanding and flex those muscles a little bit.
It definitely gives me respect for those of the like Neil deGrasse Tyson or Sean Carroll, someone who explains these really difficult ideas pretty simply. I know I don't do the best, but
it's useful. I definitely know I've learned something, and I think you're doing great. All right, guys, let us know what you think, and we'll see you next time.
Till next time.